Great, we're recording. So you can see that the way we're going to draw circuits now is a little bit different. As I mentioned before, we've been doing top-down circuits. That's kind of the way electrical engineers do things. But then textbooks often do this sort of circular approach, which does have its merits. And so we'll talk about that too. Let's just take a look at some of the features of this circuit. Get my mouse over here. So these squiggles are for resistors, or it really could be any kind of load on the circuit, like an appliance, some lights, a TV, things like that. This is the new way that we're drawing batteries. So long line and then the short line. And remember, capacitor is two parallel lines. And then here's a switch. So if this switch is closed, so right now R is not part of the circuit. But if you close the switch, then current is going to flow through it. And then this switch over here, S2, what this would essentially do would be to bypass the 10 ohm resistor. Good. All right. So we're actually just going to do, even though the units look rather short, they're really packed. So we're going to handle just the first two bullets tonight. And that'll be plenty to get you going. And then we're going to come back to RC circuits later on. All right, so EMF, this is the first time we're talking about this. This is electromotive force. And then we're also talking about terminal voltage. So terminal voltage in particular refers to the voltage across the terminals of a battery, the shiny metal parts of our 9-volt battery. And now we have a new variable, this squiggly E. So this cursive E represents the voltage that's provided by chemistry. So for carbon zinc, that's 1.5 volts. For lithium ion, it's about 3.7. For lead acid, it's 2 volts. So it really depends on the chemistry. And then I for current, we're used to that. And then a little r, which is going to stand for internal resistance. And here's what internal resistance really means. We have an E that's represented by chemistry. But in a real situation, chemistry consists of reactants turning into products. The reactants give us this oxidation reduction reaction that can generate a voltage. And then that voltage is sort of like a pressure that pushes charges through a circuit, an external circuit. But since there are actual reactants in a physical surrounding, there's probably going to be some degree of resistance. Now, typically, there's not very much resistance. But over time, as reactants get used up and are turned into products, then the internal resistance increases. And that's what happens when we have a dead battery, is that the internal resistance has become so much that the chemistry is still there, but it just can't deliver the current like it used to. So it turns out that you can only test for this when the battery is under load. So this is a good time of the year where, if you've had a car battery for a while, you might be thinking about, is this battery going to make it through the winter? Because, when it's 15 below out and you go out to start your car and that oil is as thick as sludge, it's hard on the battery to turn that motor over and get it started. And my son just got a car. He likes collecting vehicles, so he has a 2001 Dodge Viper that has most cars have a 4-cylinder, 6-cylinder engine. This one has 10. It's ridiculous, and I'm sure that his battery is not going to make it through the winter if he keeps driving it through the winter. But anyway, we'll see. The motor takes up half the car. Anyway, so when we ask the car to do something, and I'm sure you've had the experience of when you go to start a car at night, if you have the lights on already and you go to hit the starter, that the lights can dim. That's an example of a big load, and it causes the lights to dim because the terminal voltage drops. Here's how we can take a look at how to calculate terminal voltage. Right, we have a sample problem actually to do this. So I'm going to go to our agenda and take a look at a sample problem. And that one actually shows up down here. I'm going to make this a little bit bigger. So if you want to take a snapshot, you can. I'm going to repeat the details on the whiteboard. Okay, there we go. That looks good. Okay, so we have a battery with an EMF of 12. It shows a terminal voltage of 11.8 when operating 2 light bulbs that are rated at 3 watts each. What's the battery's internal resistance? Okay, well, I'm going to change camera views here. So stop share and take a look at the whiteboard behind me. Here we go. So if we start off by doing the terminals of a battery like this, and it's a box. And there's stuff inside. So with this 12-volt battery, what we know is that there is an EMF in here, and that's equal to 12 volts. And that's guaranteed to us by the chemistry that's inside, but there's a little bit of internal resistance. And then finish our connections. Now on the outside, we can hook this up to a voltmeter, which is what we did on Monday. And so I'm going to represent our voltmeter like this, a V, and we'll just leave that V connected to our battery. We know that for a voltmeter, it has a really high resistance, practically infinitely large. And then we're going to hook it up to 2 light bulbs in parallel. Let's see if we can see that. Yep. Okay. Good. And so we have a little resistance right here. So the resistance of voltmeter is essentially infinite. That means that it's not going to steal any current. So when we hook this whole thing up, then we're going to have current going through this light bulb and this light bulb, but almost no current going through this voltmeter. Now, just to emphasize this, I'm going to put a little switch in here. Here's our switch. So E, again, we call it electromotive force, EMF. And it's because of the chemistry. However, the terminal voltage, VT, equals when there's no current flowing. Right, so our central equation looks like this. The terminal voltage will equal the EMF minus the small amount of voltage lost as charges make their way out of the battery. But if I is equal to 0, then these two are equal. So the terminal voltage is equal to the EMF when no current flows. Sometimes we call this the open circuit voltage. So if you had a voltmeter and you wanted to go check your car battery, you pop the hood, you take the leads and you go like that. You're measuring the open circuit battery, open circuit voltage. So it's not really going to tell you how good the battery is. It's only when you put a load on it, then you can see what the internal resistance is. So I brought this all up in case this is just the time of the year, you know, if you're putting snow tires on, getting new oil changed, getting prepared for this natural disaster that we call winter, which Brendan doesn't need to worry about this year. And although I look forward to if you get a snowstorm in North Carolina, just to see people running around like not knowing what to do.
Oh, I love it.
Anyway, if I close the switch, then what the guidelines of the problem say is that with the open circuit voltage, we get 12. But when we close the circuit, and then the terminal voltage is only 11.8. By the way, I just think this is interesting, and I'll share it with you to see if you think it's interesting also. Have you ever noticed that when you look at power switches, you want to turn something on, and sometimes it'll say on and off, but sometimes you'll also see a symbol that's a circle or in a straight line. Ever seen that before? And you're wondering, like, which one's which? Because the circle looks like O for on, right? This is actually a convention that some folks at IBM invented many moons ago, but open circuit means there's no current flowing, and that's supposed to be off. So open circuit is code for off, and then that's where this came from. And then closed circuit, that's on, and so they were trying to show a switch open and a switch closed. That's off and on. So anyway, in case you were wondering.
I always thought it was like a binary thing,
Right, well, let's
of
go
like
ahead and put in
0
some numbers
being
here.
closed.
So 12 is our EMF. And then this is 11.8. I times R. So I can subtract 12 from both sides. And I'll get negative 0.2. Multiply through by negative 1. And then this is telling me that I times R is equal to 0.2. But there was another piece of information that we were given, which said that these light bulbs generate 3 watts at 12 volts. So the bulbs produce 3 watts at 12 volts. And so I equals P divided by V. So 3 watts divided by 12 gives me a current of 0.25 amps each. And there are 2 of them, and they're in parallel. So that means the total amount of current is 0.5. So 0.5 times internal resistance is equal to 0.2. And so I can divide both sides by 0.5, which is the same as multiplying by 2. And then so my internal resistance is equal to 0.4 ohms. Okay, cool. So you got one for the books. The internal resistance for your 9-volt batteries are notoriously large because we don't usually ask them to produce a lot of current. They're usually just, if they're driving electronics like a small radio or something like that, they don't really need very much. So I'm going to go back to our slide deck. If you want to take a screenshot of this, now's a good time. Okay. Good. Great. So we'll do a little more practice with this next week. Let's go take a look at our slide deck and see how we're doing. So we've actually already taken a look at this. So we sort of did this inductively on Monday night. So you did a great job. We set up a Google Doc, and we actually, I might want to just take a look at that. So, whoops, I did not want to do that. No harm, no foul. Let's see if I saved our data. Thought I did.
I think if you go back to, if you click back, I thought I saw it pop up.
Weird. I wonder what happened to that.
Hey, Joe.
Bear with me just for a second. Let me just take a quick peek
Brendan, can you hear me?
here. If I go into my applications and see if it remembers the last
I can hear you, Lauren.
Google
Okay.
sheet that I did. Ohms law resistors 1012. That's us. Okay, so I wanted to point something out. And just taking a look, and if you happen to have your values, that would be great. But I don't want you to miss what I'm about to do by digging through your Google Drive. So we have voltage versus current for a 270 ohm resistor. And our regression, spot on. The slope I get is 284 ohms. So that is actually the real resistor of that. It's labeled as 270, but again, that's plus or minus 10%. So plus or minus 27. And this definitely fits that. It's 14 ohms over. But I'm just going to jot that down. And so 284. So let's call that R1. All right, then I'm going to take a look at the 100 ohm resistor. We'll see how close we came there. And again, these are made by the billions. And I forgot to change the title of the graph, but I got 107 ohms. So again, that is within 10%. They're both actually high. So R2 is going to be equal to 107. Now, we talked about how resistance in series adds. And I have a 284 ohm resistor and a 107 in series. So if I add that up, that comes out to 391. And my slope was 373. So there's a little bit of a percent error there. If I was just adding what their labels are, then I'm spot on. But I really, when I'm comparing it, I should use the actual values we get from the graph. And then for parallel, why don't you do this exercise with me? I think we did it Monday night anyway. So this is that funny situation where we add the reciprocals. We add 284, 1 over 284 plus 1 over 107. And to get an answer for that, and then take 1 over that. So I get 77.7, and my regression gives me 75.9. So those are some ways that we can calculate percent error. The bottom line is that with 100 and 270 in parallel, the effective resistance of both together is less, because there's multiple pathways. And it's not half because there's more resistance in the 270 than the 100. But if they were both 100s, then yes, I would expect the resistance to be half. All right, so let's take a look at a couple of practice problems that I go to do this. I just wanted to do this to remind you about what the punchline was Monday night. Okay, let's pull up our agenda and take a quick peek. So here's the first one I'm going to do. Okay, so we have 345s and 375s connected in series. What's the total resistance, and what if they were all in parallel? All right, so fair question. Let's go off and take a quick peek at how to do that. You go to the whiteboard, take a peek. Resistors, so I'm not going to draw them all out. Take a while, but let's start focusing on some shortcuts. So 345s. So 3 at 45 all in series, and then we have 3 at 75. And we want to find out what the effective resistance is. So REQ is the equivalent resistance that's going to replace all of them. You know, equivalent resistance is really the equivalent load that happens. So right now, when I came out onto the porch tonight and I turned the light on, got my computers going, got a TV going, then Green Mountain Power, which is looking at my neighborhood, sees that the load goes up, and that means the effective resistance of my house goes down. And we'll see why in just a second. So REQ means to go R1 plus R2, and then keep on doing this. So I can certainly just group things together, and I could add 45 3 times, or I could just multiply 3 times 45. And then 3 times 75, and we'll see what we get. Let's see, that's 110, 120, so that's 3 times 120, so 360. Right. So again, we talked about traffic jams, right? If I have a traffic jam, then there's another traffic jam in front of that, then there's another one. Then it's going to take me a lot longer to work my way through here. But, and this would be great, so traffic jams, what if they opened up more lanes? And that's what parallel means. So we're going to have multiple like that. And then we know the equivalent resistance. Now I have multiple lanes to go through, so this is going to be easier to travel. So 1 over REQ is equal to 1 over R1 plus 1 over R2, and then repeating. So when I do it for this example, 1 over REQ, well, I have 3 45s. So it would be 1 over 45, 1 over 45, 1 over 45, but let's just do 3 over 45. Plus 3 over 75. Now I'm just going to do this and get a number and see how it comes out. So I'd encourage you to do this along with me. This in particular, because the last step is a little tricky. 3 divided by 45 plus 3 divided by 75, and I get a decimal, which makes sense. So 0.1067 or 106 repeating. So I'm not quite there yet. I still need to, that's 1 over the equivalent resistance. So to get this, I need to do 1 over my answer. And so I get 9.4 ohms, which is quite a bit smaller than the 45 and the 75. Is there a lot of them? All right. Thumbs up if that sounds good. Yay. Okay, let's take a look at another one. And we're actually just going to do 2 more. So I'm going to stop video and just show them to you in case you want to take a screenshot of the problems. Hi. Bye. Okay. Let's see, 8 lights connected in parallel to 110 volt source by 2 long leads, like alligator clips, of total resistance 1.6 ohms. And then if you have 240 milliamps through each bulb, what's the resistance of each? And what fraction of the total power is wasted in the leads? This is an interesting question. There's a, I think there's an exam question like this that talks about what happens when you use a really long extension cord and some problems associated with that. Actually, I have an extension cord in here. That would be good to contrast. So I'm going to stop my share here for a second. Okay. So here's the extension cord that I happen to have. And it's like this. It doesn't have a grounding hole in it. That's a problem. So I can't really plug very much into it besides like a cell phone charger or a lamp. But also you can see the thickness. This is really small. So let's suppose I took this out to the garage and I wanted to run my my radial arm saw with it, which draws about 15 amps. So if I was to do that, this pipe is too tiny to carry 15 amps. The wire is going to get hot and probably start smoking. And worse than that, because it's got resistance, then my radial arm saw that's supposed to work on 120 volts is going to see a voltage drop through this extension cord. And so it really would only see about 100 volts. And that's not really great for it to run at that lower voltage. Now, trade that with extension cords that come in different shapes. And of course, copper is very expensive. So this is just FYI. Looking at home ownership one day, or maybe currently, like to get some outdoor tools. And this is something to be mindful of. So if you have long extension cords, you really do need them to be pretty thick as well. Otherwise, there's a lot of resistance in the leads. That's where that came from. All right, well, here we go. I'm going to take a look at how this is going to sugar off. Take a look at the whiteboard. We can do a quick sketch of this. So we have 8 lights and we have two leads, and it says the total resistance is 1.6. So the leads come down like this. We have an alternating voltage source. That's how we would draw this in our new configuration. The leads have a little bit of resistance. We measured the resistance of our leads the other night. And then we have 8 lights altogether. And these are little lights. Maybe these are like Christmas tree lights, something like that. So 240 milliamps is 0.24 amps. And there are 8 of them. Three more. You don't have to drum all that. I wanted to do this because since they're in parallel, the currents are going to add, and it makes more sense when we can see them. So these are all connected together. So 0.24 amps each. And it's 110 volts for the source, and then the resistance, the two leads have a total resistance of 1.6. So this is an example of a combo circuit. And that means that each one of the leads independently is going to be 0.8 ohms. You didn't have to do this in order to be successful with this problem, but I think visually it makes a little more sense. So the 0.24 is going to be repeated for all of them. And that gives us a sense about what the total current is going to be. Right, so we have 110 volts, and then we want to see what the total current is going to be. So I is going to be equal to 8 times 0.24. Easy enough. I get 1.92 amperes. And so the source voltage is 110, but I'm going to lose a little bit of voltage across these two resistors. So the voltage drop here to here, it's going to be the same for all of them because they're in parallel. But we can take the current and we can see the voltage lost in the leads. So the voltage drop for the leads is going to be equal to I times R and 1.92 multiplied by resistance, which is 1.6 ohms. So this is what I was talking about with the extension cord. The extension cords do soak up a little bit of energy. The thicker the extension cord, the less resistance, but it's still a number. We also know that thicker, very long extension cords can get really expensive. So if I wanted to run my chop saw out by the shed out back, I need a 100-foot extension cord, and that could easily run me $70. Right, so this is a voltage that's soaked up by these leads. And I think you remember from Monday night, we had situations where some of them got a little hot because they're just quarter-watt packages. Right. So the overall power, let's see, I've got 2 L's. So voltage for the leads, that means that the voltage for the lights, I'll just write lights, is going to be equal to 110 volts minus this number, which is about 3.1. So if I put a voltmeter here, that's what the lights would say. So 106.9. Right, and the more lights that I add, the more current I'm going to draw, and the more energy I'm going to lose in the leads. But the question is, what about the power? So these are giving off heat, and they're going to lose. They're going to give off energy at the rate of P equals I squared R. So that's going to be equal to 1.92 squared times 1.6. And again, this is the rate at which these resistances give off heat. And so that's about 5.9 watts. So these are for the leads. And then P equals I squared R for the lights. But I don't really know what the R is for the lights. I do know, however, that the voltage drop is 106.9, and I know the current is 1.92. So I can also do it that way. I'm not using 110 here because I know I've already lost a little bit of voltage because of the leads. And so I use 106.9. And then the I value, which is 1.92. Running out of room here, but that's okay. And so the lights are kicking out power at the rate of about 205.2. And that's for the lights. So this is pretty close to 6. This is pretty close to 200. So the percent loss is going to be around 3%. And as I've mentioned before, this is a problem when trying to transmit electricity over long distances. This is, this is the part where I say a concept again, underline, quotes, boldface, and I just posted chapter 18 quiz. Right, so this is a problem when we're transmitting power over long distances. Like I mentioned before, Hydro-Quebec is actually thousands of miles north of Montreal. And so they're transmitting power over a very, very large distance. So the rate at which the power lines lose heat is I squared R. So you can transmit the same amount of power by having a very large V and a small I. And that benefits you because I squared R is the amount that you're losing in the transmission lines. So that's how come energy is transmitted at high voltage and low current. It's because it cuts down on the power loss. Even at that, the current is going to be several hundred amps. And so those power lines need to be really thick pipes.
Hey, Joe.
And this might be a surprise to you, like the other night, we were using wires that had insulation, vinyl insulation on them. And that's to keep them from rusting and also protect you. But they're on those big power lines that you see, there actually isn't any insulation on them. They're coated with stuff to keep them from rusting, but there is no insulation. Yeah, Lauren, you have a question?
I do, but I don't think you can hear us.
Did you lose me?
I can hear you, but you can't hear me.
How are you doing? Am I back yet?
I can hear you,
Okay.
but you can't hear me.
I can hear you now.
Oh, you can hear me now. Okay. Whew. Okay. For a second, you couldn't hear. I had a quick question. So you said that when power's transferred at high, did you say high resistance?
High voltage, low current.
Okay, thank you.
Yep. But then on the local end, we have to bring it down to low voltage, high current. But at that point, it's usually spread out over many cities, so the current's actually quite a bit less. But we'll talk about power distribution later on. That's just for that one question. Then there's a follow-up question that talks about, it gives you actually some details around the a sample line for Hydro-Quebec. So it's going to give you a length, a resistivity, and give you some data. And it's going to ask you to probably calculate the thickness of the wires, I think, something like that. Okay, we've definitely beat this one to death. All right, and now let's look at the last one. So far, things have been going pretty smoothly. But it's about to get a little heavier. Okay. And this is number 20. And we have a circuit. So here's what the circuit looks like. I'll try and draw it larger so you can see it. But I don't want to take up too much space because I'm going to need quite a bit of this whiteboard in order to finish it. That's a mess. And all the R's equal 12. All of them. Okay. So we're supposed to figure out the equivalent resistance of this mess. And it's complicated. So we definitely have a combination of series and parallel going on. So the approach is like this. We want to look for two obvious combinations of resistors in series or parallel. So let's take a look. Are these two in series with each other? Is there a single path? And the answer is yes. Because when current comes out of this one, they only have a choice to go through this one. So these two are in series. These two are also in series. But are these two in parallel? I mean, they're stacked. But the answer is no, they're not in parallel. If this wasn't here, if this was just a straight line, I'm going to put this back in a second. But if we had that situation, yes, then these two are in parallel. Current splits up, and then the current comes back together. But with this resistor in here, when the current splits up, this current has to go through two resistors and not just one. Oh, but what could I replace these two? My headset just squeaked out. Am I back? Okay, good. All right, so let's start off by replacing these two with a single resistance. And that's what our goal is. We want to just carefully break this down. So I'm going to call this A, B, C, D, and E. So combine A and C. And let's see what our circuit's going to look like. So 2 lines on equal length. Okay. So A and C, I combine them to give me 2, or I combine them to give me a single resistance. All the others are still 12 though. So this is 12 ohms and this is 12 ohms. And this I haven't done anything with, that's 12 ohms. But now this is a replacement for A and C. And so since they were in series, I just add the 2 together to get 24. Now these 2 are in series, so I can combine them and get 24. But it's these 2 that I'm worried about. So let's combine those 2. So I'm going to do that down here. Combine the 12, which is B, and 24. So that means 1 over R is going to be equal to 1 over 12 plus 1 over 24. Right, and then don't forget to do the 1 over at the end. So R comes out to be 8. What does it look like in the circuit? Well, now my new circuit looks like this. I've combined these into just one, and it has a resistance of 8 ohms. The 12 and 24 are one of those, usually we would get a decimal, but 12 and 24 are special. And so we have 12 ohms and 12 ohms. Right, these are our originals. This is D and E. And now I just have a single pathway. So clearly these are all in series. So my equivalent resistance is equal to 12 plus 12, which is 24, plus 8, so that's 32 ohms. So all of this gets reduced. In general, I'll call this circuit reduction, gets reduced to 32 ohms. So this takes a little bit of practice, and I would encourage you to try this for some of your practice work. But let me just show you where we're headed. So if I had provided you a voltage for this, then we'd actually have to go backward to figure out what the voltage drops and the currents are for all of these. That's where it's gonna become a little bit of work. So we're gonna do that, a little bit of that on Monday. But I think that's a fair place to stop. If you want to take a screenshot of this or just take a picture, welcome to. Brendan, did you bring snacks for everybody tonight?
I think I have enough to share.
All right, good. So let's go back to. Good. That's a good place to stop. We have a few more classes, 3 more classes to cover this material, but that's enough for you to get going. I'm going to post a problem set in Mastering Physics, and so you could do that instead of doing, and I just want to see how you feel about it. We'll do that for a few weeks, and then we'll decide which way we want to go for it.
So the Mastering Physics homework is due on Monday, and then the Jumbo series that you posted a while back that we started, I think it was during our first lab we did together. Do you have that posted with the correct answers? Or do you have like?
No, I don't have the answers posted yet.
Okay.
Yeah, but It'll probably happen.
Okay, because that's gonna
High
be
likelihood.
on the quiz for chapter 18. You showed us, so,
Yes, there's one. There's one of them.
okay. All right, awesome, thank you.
Yeah, good. Yeah, so just to be clear, you'll get a notification about a mastering physics assignment. It's not required, but you could do that instead of doing the other. And then I'm curious because I want to see what it looks like on my end when I get it back. So they haven't really given us a lot of training in it. So that's the plan. Any other questions? Yeah, okay. All right. Well, have a nice weekend. And if you have any questions on the chapter 18 quiz, just give me a shout.
Awesome, thank you.
Sounds good. Thank
Right.
you.
Thank you for class. Have a
Yeah.
good weekend.
You bet.
Monday.
You too.
Have a good weekend.
See
See
ya.
you Monday.
Take care.